So we have covered quite a bit in the case of finite volume time domain. So we have looked into the basic formulation starting from the computational fluid dynamics perspective. We have given certain justifications on why it is working, what are the formulations, internal physics in terms of hyperbolic formulation, what are the eigenvectors and eigen values, and also we have given certain solid foundation on how to model this for a 3D problem or a 2D problem. And later on we also discussed on the domain truncations. We have discussed quite advanced techniques starting from the Beronje PML to also applications using uniaxial PML. And in the applications we have shown quite interesting problems starting from simple waveguide truncation to horn antenna to a more complicated, really complicated problem, which is even for commercial solvers a big challenge. So that being said, the problem comes to one simple question. So finite volume time domain method is a very unique method. It has certain advantages compared to finite element method because we don't need to do a matrix inversion. If you are working in the frequency domain, you normally end up in doing matrix inversion, and also time domain problems. It's very difficult because sometimes the formulation of finite element method is implicit, so still you will come inevitably to a matrix inversion issue. That being said, the finite volume time domain method avoids all this kind of complication, and it has certain beauty. But there is something hidden here. The hidden thing is it has certain limitations, and these limitations are not openly discussed in public literatures. We wanted to make sure that when you understand the method, you also understand the limitations of the method, where it is useful, where it is not useful. So we will in this particular module discuss on the limitations of the method, both from the numerical accuracy point of view and also from the computational cost point of view, and also we will discuss why it is that way, how we can go forward, what are the future areas of research that is going on, and also give certain directions for further research. So that being said, let's start with the challenges. We said the method is having numerical dissipation. So what I mean by that is, when you are talking about a simple waveguide problem where you are talking about wave propagation, you will see that along the x-axis the amplitude of the wave, if red is the exact value, the blue is the numerically computed value, you will see that the amplitude decreases over a period of time. So that is the numerical dissipation what we are talking about. In other words, numerical error related to the amplitude. The other one is you will also have dispersion where the amplitude might not be affected, but the propagation velocity of the waves is not actually mimicking or replicating the exact value. So you will see that there is a difference in the wave velocity here, or the propagation speed is different for different things, for the exact solution versus the numerical solution. In the case of finite volume, the biggest challenge is the numerical dissipation. Of course, I have here exaggerated the numerical dispersion in a way to showcase the meaning of dispersion here, but in the case of finite volume we have dispersion, we definitely have dispersion, but this dispersion is not as exaggerated as it is shown here. This is just for the example what we have shown here. The dispersion value for finite volume time domain is what we have, constraints or within the limitation of numerical accuracy what we need, but this one, the numerical dissipation, or in other words amplitude decay over a period of wavelengths, is something that is the biggest limitation of the standard finite volume method. So when I say standard finite volume method, I am talking about values of the E field and H field stored in only one particular location. In other words, as we remember, if you have a triangle represented like this, in the case of finite element you might have values that are stored in the nodal values, or you can have values also stored in the edges. So then it will be called as edge element or a nodal element. But in the case of finite volume, the values are stored only in the center. So standard FVTD, the E field at time n and H field at time n, they are all stored in the center. So this has certain advantage because numerically it is less heavy compared to the finite element method, and also we are able to compute the value of E and H field at one point in time and one point in space. So in other words, it helps you to be more accurate. Instead of staggering in space and time, you do not need to do that, but it has this disadvantage of dissipation. So that is the aspect of dissipation this someone who is starting to work on finite volume time domain should be aware of. If you are not aware of that, for some problems you might end up in difficulty in getting the right accuracy you want. One way to solve this is you go from lambda equal to 10 to lambda equal to 20 or 30, but this again has this trade off for computational cost versus accuracy. So this is something that as a numerical scientist who is working in computational problem, you have to make a better informed decision on what is good and what is not good for your particular problem. And that being said, what are the ways in which this can be understood is, since E and H field are co-located, the co-locating itself does not follow the duality. What I mean by duality will become clear in our next module on algebraic topology and other stuffs. For now you can understand E field and H field have different topological characterization. That is something will be destroyed in the case when you make them co-locate in space and time. In other words, when you associate them both to a particular point, you are inherently killing the dual nature of E and H field, and also the topological connection of E and H field. And the second thing is, in the case of finite volume method, although you do not see the difficulty that the curl of the divergence or the divergence of the curl, it should be equal to 0. It is difficult to verify because there is so much dissipation is going on. This particular condition, even if it is not equal to 0, will not be a huge problem, but still this is one of the things that we need to understand, because the spatial discretization does not have the duality nature, and also it is very difficult to verify this one. As I already told, there are certain geometrical association of vectors, whether it is E field or H field. Some of the vectors are associated with line, some of the vectors are associated with surface. For example, E field is always associated with the line, but in the case of finite volume method, we are associating E and H field to a point. They are values stored in the point, but there is an association between E and H field to the line, which we are not taking into account. Again, the value of the fluxes are associated to surfaces. This is something that we will see in the next modules, but still what I wanted to do here is I wanted to give you a direction in which we are going to go in the next modules, which will take into account the inherent duality between the electric field and the magnetic field. Not only that, it will also use the topological objects. We are interested in making sure that the field quantities are associated with those topological objects. So topological objects could be a point, could be a line, could be a surface, or could be a volume. So this is what we will be doing in the next series of lectures. Before we finish off with this module, what I wanted to give is some additional material. So this is my PhD thesis, which is also available online using this link, or you can just Google search this particular topic. It basically discusses all the topics and all the equations and all the things that we have discussed in this module. So it is the accurate domain truncation techniques for time domain conformal methods. The most important method we will be focusing here is the finite volume time domain method. It is equally applicable for higher order methods like discontinuous Galerkin or higher order finite element methods. And also one another paper that is interesting to see is the uniaxial and radial anisotropic models for finite volume Maxwellian absorber. It is also available on the IEEE transaction. If you are interested in open access, I think this particular thesis will give you all the things what we have discussed. So with this we can come to a stop. We have covered pretty much the entire tool set of finite volume time domain method, and we will focus on other methods. Understanding the limitations, we will take it to next methods, how those methods can help us resolving those issues what we have with finite volume time domain method. With this I would like to conclude this particular module. Thank you.